What's up, you scholars of enlightenment? Astronomers have unveiled the first image of the supermassive black hole at the centre of our own Milky Way galaxy. Now, this result provides overwhelming evidence that the object is indeed a black hole and yields valuable clues about the working of these giants, which are thought to reside at the centre of most galaxies. Now, the image was produced by the global research team called the Event Horizon Telescope Collaboration, and it uses observations from a worldwide network of radio telescopes. The breakthrough follows the EHT Collaboration's 2019 release of the first image of a black hole, which was called M87 star, at the centre of a more distant Messier 87 galaxy. So, to help us dig into that image and understand exactly how it was made, what it shows and why it's important, we welcome back the always phenomenal Dr. Dan Wilkins. Dan, how you doing?
Pretty good, Sam. How are you?
Yeah, I can't complain. Not too bad. The weather's finally getting a bit better over here, so it's all good. So just to remind everyone, Dan's been on the show before, but Dan is an astronomer and astrophysicist at KIPAC, where his research focuses on how material spiraling into supermassive black holes at the center of a galaxy is able to release huge amounts of energy and power some of the brightest objects we see in the universe. So, who better to help us go through these amazing images? So, Dan, I don't want to waste your time. I want to get straight into this. What are we seeing in this amazing image? What are we, because we can't see the black hole, what are we seeing?
Yeah, so what we're looking at in this image is fundamentally the ring of hot gas that is in orbit and slowly spiraling into the supermassive black hole Sagittarius A star in the center of our galaxy. So that ring of light is the emission that we're seeing from that hot gas. And then that dark ring in the middle is the shadow of the black hole itself, the black hole being that region of space where the force of gravity is so intense that absolutely nothing, not even light, can escape.
So what kind of radiation is coming out of here? So I guess you've got infalling matter, which is getting up to very high speeds, close to the speed of light. I guess it's getting ionized. Is that the radiation that's coming off? Because we've got ionized particles, charged particles moving in tight circles, or is it just due to the heat of the material?
Yeah, that's exactly right. So the Event Horizon Telescope isn't looking at visible light like our eyes can see. It's looking at submillimeter radiation. So this is electromagnetic radiation that's somewhere between radio waves and microwaves on the spectrum. And this emission that we're seeing is coming about because, as you say, this hot gas has become highly ionized. And we actually have magnetic fields that are tied up with all that gas in the black hole. So we're seeing synchrotron emission, it's called, where the electrons are whizzing around those magnetic field lines, traveling around in circles, and that's producing the emission that we're seeing.
Amazing. It might be a silly question from me, but I'd have expected, because we're in the plane of the galaxy with this black hole, that we wouldn't see this beautiful ring. You'd maybe see some sort of a flat sheet. Is there lensing going on here that makes us see this sort of projected image rather than seeing that sort of disc, flattened disc?
Yeah, I had pretty much the same question when I first saw this image. So what we think we're looking at here is
I don't know if this image helps at all or makes any consequence, but
yeah, so that's what you would see if that disk of gas that we were seeing around the black hole was edge on to us. So if you took the black hole away, we just had a disk of gas, it would look completely flat.
Yeah.
And then because we've got that black hole in the middle, that black hole is curving space and time around it. So it acts like a massive lens, distorting the image and producing that loop structure that you're seeing in the picture. But actually, the models that they use to try and explain the image of Sagittarius A star that we're seeing, it looks like those models say that's not what we're seeing. Yeah. We're actually seeing a disk that's not edge on, but it's face on, which is kind of weird because, as you said, we're in as far as we understand, the Milky Way is a spiral-shaped galaxy, flat disk of stars, and we're out here living on the edge. We're looking through that disk to the black hole in the center. So we'd expect the gas around the black hole to be in the same alignment, but it looks like it's not. And I think that's a really interesting puzzle that we need to figure out.
Interesting. So there's more things to work out. What's the sort of scale? So I remember last time we had you on, we were talking about supermassive black holes. What's the scale that we're talking about here with this image, and in general with Sagittarius A star? There's the image that you were talking about where we're out in one of the spiral arms, and this is in the middle of our galaxy. How big is this thing when we're looking at this image to get an idea? What could we compare it to?
So if we're just looking at this on the sky, it would look about the same size as as the Event Horizon Telescope team, actually the analogy they use themselves, we've got this donut of gas. Yeah. This donut of gas as we see the image on the sky, is the same as if there was a donut on the surface of the moon.
I've seen, by the way, Krispy Kreme are offering a free glazed donut if you go and take it. I think if you take an image of this in, or you mention it when you go in. So just a public service announcement for anyone to use that analogy.
Yeah, I'm just sorry that I'm traveling at the moment. I'm not at home in California to redeem my free Krispy Kreme donuts. Exactly. But yeah, so this thing that to us looks like a size of a donut on the surface of the moon, it looks so small because it is 27,000 light years away from us. But if we actually were to go up and measure how big is this thing, the radius of that black hole in the center, or at least I shouldn't say the radius of the black hole, rather the radius of the event horizon. So that's the region of space around the black hole that light can't escape from. Yeah. For a black hole about the size of the one that we've got in the center of our galaxy, it's going to be about 4 million miles or so across.
I think we had a little bit, people have tried to do these comparisons. I think they said something like, so what have they got here? There's the Earth's orbit out at 150 million kilometers as a scale of the size of this thing. So that gives you some idea. Here's the sun's radius in the center here. Here's the event horizon, and this would be the Earth's orbit relative to the sun, to give some sort of idea of the scale, which is kind of very difficult to get at. What's the mass of this thing?
So our measurements indicate that black hole in Sagittarius A star is about 4 million solar masses. So that's 4 million times the mass of our own star. So it's pretty big. Not the biggest black hole we've seen. In fact, it's quite a bit smaller. It's 100 to 1,000 times smaller than M87, the first black hole that the Event Horizon Telescope imaged. But it's still pretty big compared to anything around us in the galaxy.
Yes. So we're gonna get onto that comparison. So I wanted to ask you. So we've had this picture of M87. I think it was 2018. What is new here? Because I remember, if we go back to a couple of years ago, 2020, I believe, we had the Nobel Prize for a very super compact object in the center of the galaxy, and it seems that came from observations of the orbits of stars there. So why is this, what have we added to the knowledge base here, and why is it such an important observation?
So I think the biggest thing that we're seeing with this new image of Sagittarius A star is that we actually now have an image, a first-hand image for the first time of the black hole in the center of our galaxy. So Andrea Ghez and Reinhard Genzel, using respectively Keck telescopes and the VLT, they were looking not at actually the black hole, but they were following the orbits of the stars in the center of the galaxy. And they were able to figure out that by measuring how big those stars' orbits are and how quickly they're traveling, in order to hold those stars in orbit in the center of our galaxy and stop them just flying off into space, we need something massive in the center of the galaxy. It needs to be massive enough to provide enough gravity to hold the stars in, but it needs to be small enough that those stars don't crash into it. And as far as we understand general relativity and the laws of physics, something that heavy and that small can only be a black hole.
So this explains the sort of the sort of hedging wording, doesn't it, here in the giving of the Nobel Prize. So they say it's for a supermassive compact object, which everyone's kind of assumed is a black hole, but could have been something we've never considered, or some bizarre sort of distribution of matter that we don't know about. But actually, this is sort of the clincher now, that we can physically see that this is a black hole.
Yeah, we're seeing that shadow, that dark region in the image that we're seeing. Yeah, there's no light escaping from there. There's not like a weird sort of star there with some sort of luminous surface.
Yeah. Makes sense. So we've basically updated and closed that little bit of a potential loophole. So the question becomes, how did we manage to make this image? So you've said this is 27,000 light years from Earth. It's a tiny pinprick on the sky. How do we go about making an image from the Earth of something so tiny and getting such a beautiful image as this?
So the key here is to really understand what we need to take high resolution images of the sky. Now, by high resolution, what I mean is that we can actually see small objects. And if we've got two small objects close together, we can actually see that they're separate objects and they don't just blur into one. And the laws of physics tell us that to do that with a telescope, the smallest object that you can resolve depends on the wavelength of the light that you're observing. And here we don't get to choose the wavelength. That's the submillimeter sort of radio to microwave radiation that we've chosen to look at. So the only other thing we have to control our resolution is the size of the telescope. And what you need to see a donut on the surface of the moon is a telescope about the size of the planet Earth. So the question now is, how can we possibly build a telescope that's the size of the planet Earth? But it turns out that we've got a really cool trick when it comes to building telescopes. This is something that astronomers call interferometry, and this was something that was really pioneered with radio telescopes, that if you have two telescopes some distance apart and you connect them together, they behave like a telescope that is not as big as each of the individual telescopes, but in terms of their resolution, they behave as if the telescope is as big as their separation. So by spreading telescopes around the world, and by combining the data from all of them in the right way, and using very clever algorithms to actually combine that data, that actually to account for the fact that we don't have a whole Earth covering telescope, we've just got telescopes dotted around the Earth, we can reconstruct that image as if we had a telescope with the resolution as big as the planet Earth.
Absolutely amazing. I think they said in the article 300 researchers, 80 institutes, 8 telescopes, some all over the world. So we've got a little map here, even one down at the South Pole. So really a global effort with a hell of a lot of scientists involved. And you mentioned there that they combined a lot of images, so we can kind of see that if you go into the paper. They took a hell of a lot of images. I think they were talking about tens of petabytes of data, and then essentially they filtered down how many times certain features appeared, and then made this conglomerate image to get the best image they could of this object. So very, very difficult to do, very, very interesting. I'm hoping to write up a bit more on how they did that, because there's sort of 5 or 6 papers they put out that just shows how difficult this measurement was to make. And that sort of leads into my next question as to, in 2018, we had the image from M87 star, and it's taken, 3 to 4 years to get this image of the supermassive black hole in our own backyard. Now, naively, very naively, that would seem like a simpler thing to do. Why is it taken us so long to get the image of this black hole when we had the one from M87 a few years ago? I believe that the observations that the current image is based on were taken around the same time. So it seems that there's been a little bit of a lag there.
Yeah, that's right. And the reason is to do with the size of those two black holes. So when you have gas in orbit around a black hole, the gas that's in orbit as close to the black hole as you can possibly orbit before you are doomed just to plunging into the black hole, to stay on that orbit, you need to be traveling at half the speed of light. Yeah. So we've got gas whizzing around this black hole at half the speed of light. Now, the black hole in M87 is 100 to 1,000 times bigger than the black hole in Sagittarius A star. So that means that gas has a lot further to travel. So in M87, the image, so we're not looking at just a calm day. Yeah. It's not a calm cloud collection of gas around the black hole. There really is a massive storm brewing there. And in M87, the image is changing very slowly. So when we observe it, it's almost like we're getting a snapshot, a single photograph. But in Sagittarius A star, because the gas is traveling essentially at the same speed, but the ring it's traveling around is much smaller. We're trying, it's like trying to take a photograph of a horse race with a long exposure camera and trying to figure out where one horse ends and one horse begins.
I think they said it's like trying to take an image. Another analogy they used was trying to take a picture of a puppy trying to chase its tail. You know, if it's going around in a very small circle, it's so difficult to get the one snapshot that you want that represents everything that's going on.
Yeah, so I think the really amazing achievement of the EHT team that took us from the M87 image to the Sagittarius A star image is they've come up with new ways of analyzing this data to account for the fact that this image is changing so quickly. Because remember that, again, we're not taking a true photograph here. We're having to reconstruct the image from these telescopes that are on opposite sides of the world and putting the data together after the fact. So just by having the fact we have to combine these distant telescopes with the fact that the image changes so quickly makes it a much bigger task to get that.
So you have to consider where those telescopes are, when the image was taken, how they fit together, what the state of the black hole was at that time. So many different things that you have to account for in making that conglomerate image. I believe they also had to do a lot of simulations as well to try and understand what was going on. So this took a hell of a long time. And when they do these simulations, we get something that looks reasonably like what we would expect. But you said there were some differences. Do you want to kind of elucidate on that a little more?
So I think the key thing here with so what we're trying to do here is we've got simulations of gas traveling around a black hole that we use to predict what these Event Horizon Telescope images would look like for a whole different set of setups. So we try out different masses of the black hole, different rates the black hole is spinning at, different angles that the disk of gas is aligned with respect to our viewpoint. And the way that we're able to learn about the black hole and the gas is by seeing which of these simulations most closely matches the image that we've got. We sort of have, we don't just have the Event Horizon Telescope images. We've actually been looking at Sagittarius A star for years with loads of different telescopes. We've got infrared telescopes, visible light telescopes, and huge amounts of data from the Chandra X-ray Observatory that's been looking at the high energy X-ray emission that's coming from this same gas and these same flares that are around the black hole. So it's actually quite complicated to find which one of these simulations not just matches the Event Horizon Telescope image, but also
the entirety of the data.
All of this data. So they can get pretty close. As far as I understand, there's a few things with just the puzzle is just how the emission varies over time, how the emission flickers over time. None of the simulations quite match the full set of the X-ray and the Event Horizon Telescope data. But that's okay. I mean, we know there's physics missing from these simulations, particularly turning the gas into the light that we see is a really difficult aspect of these simulations, and there's a lot of physics that goes in there that's still being refined. So I think they've done a pretty good job, and there's a huge amount we can match, and just gives us something to work on over the next couple of years to knock the final pieces.
Keeps you in business, so that's good. There's always more to do. One other thing before we move on from the kind of difficulty of doing this measurement, are there intrinsic difficulties with the fact that we're looking at something that we're in the plane with, rather than looking at something like M87, which is out there projected in a different way in the sky? Does that add its own difficulties as well?
Yeah, so as the light, or in this case, the radio waves, travel through the interstellar medium, so that's the technical term for the gas in our galaxy that's sitting between all of the stars, it gets scattered on its way to us. And particularly radio waves suffer particularly strong scattering when they travel through the interstellar medium. In particular, different wavelength radio waves end up getting scattered by different amounts. So in any type of radio astronomy, particularly within our own galaxy, there's a huge amount we have to account for with what happens to these waves on their way to us.
So putting all that together, we have scattering because we're in the plane with this thing. We had time to make these simulations. There's a lot of variability. Putting all that together gives you an idea of why we've had this time lag between M87 and this current image. So there's a lot of extra difficulties to doing this in our own backyard. Now, having got this image now, that begs the question: how does Sagittarius A star compare to other supermassive black holes? Because from what I've been reading, and you're far more of an expert about this than me, so maybe I'm being unfair to Sagittarius A star, it seems fairly unremarkable relative to some of the things that perhaps you look at with with flares and with highly energetic jets and with corona and things like this. Is it quite a quiet supermassive black hole?
Yeah, so Sagittarius A star, compared to some of the black holes we look at, I mean, a lot of the black holes I study in my own research, I mean, they're feeding on gas at a rate of something like 100 Earth masses, 100 times the mass of the Earth going into this black hole every single year. And as that gas gets crushed together, as it falls into the black hole, it's releasing enormous amounts of energy, whether that's light and X-rays, or whether it's a jet of plasma that's being shot out into space that reaches far beyond the galaxy. And actually M87, the last image from the Event Horizon Telescope, that's one thing M87 is most famous for. It's got this impressive jet of plasma traveling almost at the speed of light that goes far beyond the whole galaxy that this black hole is living in. But Sagittarius A star is much, much quieter. It's not to say that it doesn't feed on gas. We know from when we point Chandra at the X-ray telescope, we do see these little flares and flashes of X-ray emission. And occasionally there are little flashes that go off around Sagittarius A star as little bits of gas get captured by the black hole, get ripped apart and get swallowed up. I mean, occasionally as well, I mean, you get even bigger clouds that look like they're going to fall into the black hole. I remember few years ago, we all got excited when this really quite big cloud of gas was heading straight for the black hole in the center of our galaxy. So all eagerly awaiting this thing to get ripped apart and create a nice firework display for us, only to find that nothing happened.
Is it good for us that it's quieter? Does it? What's the or does it, well? I don't imagine it causes any problems, but in terms of the fact that we're here, the fact that the Milky Way developed in the way that it has, is it good for us that this is a quieter supermassive black hole?
Today, yes. So when we see these supermassive black holes swallowing gas and shining in other galaxies, so things called quasars, and there's actually so much light coming from the black hole in the center of the galaxy that it outshines all of the stars in the galaxy as far as we see it from Earth. So if you're particularly on a planet in the inner parts of that galaxy, yes, it's going to be very difficult to develop life there. And if you went on vacation there, you'd probably get quite an impressive suntan. But actually, there's a more subtle point here, and that's that we actually think every supermassive black hole, including Sagittarius A star, goes through this bright, active phase at some point in its history while the galaxy's growing. And the energy that it's able to spit out in that phase, it turns out if we could take all the energy coming out of the quasar and equally divide it among all the stars in the galaxy, you could blow the galaxy apart. It's enough to overcome the force of gravity holding the galaxy together. And what this tells us is that if you've got this galaxy that's growing early on in the universe from gas falling into it, and then you've got this supermassive black hole in the center growing as gas falls into that, which will be shining brightly as it grows. This supermassive black hole in the middle of the galaxy is able to actually influence the growth of the galaxy it lives in. So we think that supermassive black holes in the center of galaxies play a really important role in the growth of the galaxy, in particular, making sure the galaxy doesn't get too big. And then eventually it runs out of fuel, it shuts off, and leaves a supermassive black hole like Sagittarius star that just sits fairly quietly in the center of the galaxy. So it's, yeah, good job that our black hole's not active today, but it's probably quite important for our existence that it was active in the past.
So maybe maybe in the past it was a little bit more active, but it's reached its older years, and it's calmed down a little bit, maybe like most humans do. So
yes,
very, 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 very interesting. So that brings me on to the sort of final question that I had is, and you mentioned there that the supermassive black holes are very important for galactic evolution and galactic development. What are the major impacts on other areas of studies that we've got from these images? So we now have images that look very similar from two very differently sized black holes, right? So if we do that comparison, you talked earlier about Sagittarius star being 4 million solar masses. We've got Messier 87, which is 6.5 billion solar masses. Very different sizes. Is that important for us to cover a very different range of black holes and see that the behavior and the images seem to be very, very similar?
Yeah, absolutely. Because one of the fundamental predictions of general relativity is that all black holes should be fundamentally the same.
Yep.
Up to 3 parameters. There are only 3 parameters you need to describe any black hole in the universe. That is its mass, how fast it's spinning,
okay,
and whether it has an electrical charge.
Okay.
But we can ignore the electrical charge, because if you have a black hole sitting in space that's got a negative charge, it'll probably just pull some positive charges in and it'll neutralize that. So we think that every black hole should just be described by its mass and its spin. So what we have here is a black hole that is 4 billion solar masses and one black hole that is 4 million solar masses, so a factor of 1,000 difference in mass.
Yeah.
And we see that fundamentally these images look the same. They look very similar, except one of them is 1,000 times bigger than the other, because the black hole is 1,000 times more massive, exactly as Einstein predicted. So yeah, the similarity of these images and the shape of that ring actually lets us test fundamentally our theory of gravity, which is general relativity. And so far, GR has passed all the tests we've thrown at it. And again, with this image, this looks exactly like a black hole that GR predicts.
So Einstein is still winning all this time after his...
yeah, he is. Yeah. We keep trying to prove him wrong, but we've not succeeded yet.
Amazing. Is there anything you talk there about? We can essentially explain these black holes in terms of those 2 parameters, their mass and their spin. They've got no hills and valleys, things like this. Once we have those 2 things, we're kind of there. Is there anything else that we'd like to find out about Sagittarius A star? You talked about the infall rate of matter. Is there anything that's still a mystery about the black hole at the center of our galaxy that we want to find out more about?
Yeah, so other than doing these more precision tests of GR, making sure that absolutely everything is in line with GR and making sure seeing if there's any evidence that Einstein was even the tiniest bit wrong about black holes, there's a lot we can learn here about the gas that's falling into the black hole. We've got this active black hole in M87 launching this huge jet. And we've got our quiet black hole that's on this very strict diet, something like the equivalent of a human eating a grain of rice every million years, I think the EHT team said in their press conference. But one of our big mysteries is what exactly happens to that gas falling into the black hole to produce these bright light sources that we see? How does a black hole, maybe paradoxically, produce some of the brightest things we see in the whole universe? So by looking at these rings, looking at this gas, looking at the emission we're seeing from this gas, how this gas is moving, and how this gas is interacting with the magnetic field around it, we can learn fundamentally how black holes power some of the brightest things we see in the universe. And we can learn about what changes as the black hole settles down to leave the quiet supermassive black hole that we have in our galaxy today.
Amazing. So, very final thing I had was, where do we go from here? So we've had M87 star, we've now had Sag A star. What's next for the EHT? What can we expect to see more and more of these images, and we start to fill out that population? Maybe look at an intermediate size or one that's even larger. Where are they planning to go now? Do you know?
So in terms of actually imaging the shadow of the event horizon, the black hole, it turns out that unfortunately Sagittarius A star and M87 are the only two that are big enough that we can actually see the shadow and the ring. Other black holes are either smaller or they're too far away. So even with the amazing resolution of the EHT, we still can't quite resolve the shadow of the event horizon. But that's not to say there's nothing we can do looking at other black holes. EHT have already produced spectacular images of other AGN, active galactic nuclei, black holes feeding in the middle of galaxies, where even though we can't see the shadow of the black hole, we get amazing detail of the jets that black hole is launching and really zooming in on the part of space where we think those jets are launched from. So there's a huge amount we can do there. And even just with M87 and Sagittarius A star, there's more and more that we can get from these observations. One of the things we're still waiting on for Sagittarius A star is seeing not just the intensity of the light, but what's called the polarization of the light in that image. So that's the direction that the radio waves are oscillating in space. And that polarization lets us pick apart the magnetic fields around the black hole and really get to grips with the fundamental physics of the emission that we're seeing here.
Amazing. Anything from, it's the sort of elephant in the room at the moment. Anything that the James Webb Space Telescope can help us with on this? As it comes into
so JWST isn't going to be able to resolve any of this structure, but one thing that we will be able to do with JWST is look at the flares that are happening. I already spoke about how this gas is like a big turbulent storm. We see lots of flashes, lots of flares, lots of fireworks going off in the galactic center. And the infrared is one of the really good wavelengths. Along with the X-rays, the infrared is a really good wavelength to study these flares. So by looking at these flares and how they light up and how they fade away with JWST will be another really important piece of the puzzle to figuring out what's going on here.
Amazing. Had one question from a viewer, which I guess you've kind of given the answer to already. Actually, they said, "Will we have any opportunity to see two black holes become one?" I guess if we're only allowed to see these two, we're not going to have M87 merge with our own. So I guess we're not going to be seeing anything like that.
Yeah, probably not. Our best bet to see that would have been if one of these turned out to have a binary pair hiding in it. But yeah, unfortunately, I think we're not going to be able to see with the HT binary black holes merging. But instrument called LISA, which is the next generation gravitational wave measurement. Yeah. Observatory. LISA will be a space-based gravitational wave observatory. So upgrading from the ground-based LIGO observatory that we have at the moment, LISA will be able to see supermassive black holes colliding with each other and merging, not through light, but through the ripples that collision leaves in space and time.
Absolutely amazing. Dan, thank you so much for taking the time to go through this with me. It's a really amazing piece of work from the collaboration, and I've really enjoyed hearing your thoughts about it and learning more about it, and especially on a Friday afternoon. Thank you very much for taking the time. We really appreciate it. I want to point you to Dan's work and Dan's socials. I'm going to put them down in the description, so head over there and find out more about amazing black holes. Dan, is there anywhere you'd like to send people to find out more about these amazing phenomena? People are always fascinated by black holes.
I think the best place to look at the moment is the Event Horizon Telescope website itself. So if you just Google Event Horizon Telescope, there is an enormous amount that you can see there, from the press releases, the images, and the stories. And if you just want to keep following links, there's a both on my social media and my website as well. I have descriptions and links to websites that you might find interesting.
Yeah, there's some amazing images. All the papers are there if you want to follow them up. I'll put all the links in the description. One I particularly liked was I think it was is it Heino Falke who kind of gave a prediction of what this would look like about 20 years ago. And this is an amazing time for him to see the observation from that prediction back in all the way in 2000. So there's an amazing amount of information, amazing images, amazing human interest stories. I'll link them all down in the description. So head over to those links and find out more. There's an incredible amount of amazing science going on here. So Dan, again, thank you so much. Have a wonderful weekend. I know you're heading back to the States soon, so have a great trip as well. And hopefully the next time something amazing comes up in the field of black holes, we can have a chat again.
Yeah, be a pleasure. Thanks for having me, Sam.
Always a pleasure, buddy. Have a lovely weekend. I'll talk to you again soon.